Okay, hello. I'm Luigi Freda. I'm going to talk about VSLAM. First of all, thanks for the invitation, Alejandro and Professor Michael Milford. So let's go. So just a very quick introduction, what I'm focused on. I'm currently a principal perception engineer at Dexory. My focus is on SLAM, state estimation, perception, and all the related tools. So VSLAM, why? Let's start with a bit of motivation. So it started in 2019, and I started teaching a course of SLAM and spatial AI. And the starting motivation were basically we wanted to compare classical and learning-based features, rapid integration and evaluation of all these assets that were coming up, and above all, reproducible research with many data sets, and Python. Why Python? Because it's faster for prototyping, and there is a very rich ecosystem with deep learning. Challenges. So how many local features did you see? I mean, there are quite a lot, and each of them come with its own Python environments, and there is fragmentation, PyTorch, TensorFlow, and you know what I'm talking about. Then, how many datasets? C++, Python, both, and how many libraries? So just, I mean, for the backends, G2O series, GTSAP, is SE, Sync, and Python environments, Docker containers. And there is a big, I think there is still a big reproducibility bottleneck. So we have high entry barriers, hard to reproduce experiments, and everything is always starting with a build and configuration issues. And you may be wondering, well, you have it too on pySLAM. Yes, it's true. It's a big challenge to avoid them. And of course, we have a lack of modular SLAM stacks and standardized baselines. So, like, there is nothing like, as far as I know, a big SLAM core library that we can use for building many different new baseline and so on. So there is need for modularity, extensibility, and reproducibility. So the goal and design principle, as for modularity, there are the objective was to have modules for features, both local and global, loop closure, volumetric integration, semantic mapping, and that prediction. Some of them came up along the way. And for extensibility, so the design is just to use some base classes, and so to be able to have multiple interchangeable baselines. Since there are many Python environments, the objective was to have a single Python environment that could host all for instance, local features, and have one instance script. Everything is done with a single line for installing and for downloading something. Cross-platform support, of course, Linux, Mac OS, and also Windows, and Docker support. One important thing is also to be able to fully access the source code, I mean, from core modules to foundational dependencies, and handling many datasets, and to be able to save, load the map, and also to evaluate and have generation of reports and so on. So key features at the present time, the pipeline is able to support monocular, stereo, and RGBD configurations. There is support for actually both local and global features. There are many loop closure detection methods, pluggable backends, both G2O and GTSAM are supported. Then volumetric mapping is supporting TSDF and Gaussian splatting. There is a depth prediction with different models, both monocular and stereo depth prediction. And there is semantic mapping, and we have actually map saving and reloading, and acceleration via C++ with PyBind 11, and of course evaluation tools. Supported dataset. At the present time, more than 10 datasets are supported, and there is a list, and the list is growing. Apologies, the time is very compressed, so I'm going to to go fast. Maybe we can talk later. So the SLAM pipeline. So tracking, local mapping, and loop closing follow basically the paradigm of RSLAM-2. More or less, the scheme is the same. Of course, there is more flexibility for hosting different local and global features. And the new modules coming from with semantic mapping and volumetric integration are basically processing the output keyframes that comes out from local mapping. This is just to say that there is support for both processes and threads in Python for convenience. And yeah, so a couple of deep dive. So feature tracker, all the design, all the design is factory-based driven. So there is a factory. There are different types supported. Each type basically instantiate a different class. There is implementing on the top of a base class. So for instance, here we have the feature tracker factory, and we have the feature tracker. There is a base class, and we have different possible instances. The feature tracker has the feature manager. That is for extracting the key points and the descriptor. And then we have the feature matcher. For the feature matcher, the same design, a factory, different types, and then you go to the to build something on the top of the base class feature matcher. Loop detector, there is support for classical approaches and also deep learning based, and everything here is based on basic class loop detector base. And I inherited many tools coming from PPR tutorial, and I want to thank the author that are here. For depth estimation, as I said, there is support for both monocular and stereo approaches. So there is depth editing, depth pro, and so on. Volumetric integration, we have basically two implementations, TSDF and Gaussian splatting. And Gaussian splatting is based on the work of Mono.js from the Davison team. Semantic mapping, that's a work from David, that is here, and is going to present his work with a poster later. So excited about that. Thanks for this contribution. So it's important to say that there is possibility to have some automated evaluation. So basically, you can configure a JSON, put some dataset and presets. Preset is a configuration of the parameters for all the methods that you want to use, and an automatic report generation will be performed. The output are in LaTeX, HTML, and PDF, of course. And last but not least, there is a lot of py bindings, pybind 11, so visualization helper to boost performance in visualization, also perception estimation, feature extraction, and post-estimation method, and all the classic loop closure methods like dbow, ibow, OB index are basically created from C++ via pybinding 11. And then there is support also for custom factors with both GTSM and G2O. So why use pySLAM? So because it's fast and flexible for rapidly prototyping, and is built actually to allow you to experiment new components, which I think is pretty useful if you want to have a shot on some new cool approach. And evaluation is easy. There is automatic generation of metrics and the report. And the mapping allowed to save and reload the map. And of course, it's built on the shoulder of giants. Many modules are inherited, integrated, and they are there for you, of course. Limitation. Limitation, the method the main approach, current SLAM pipeline is basically just using indirect tracking. Of course, the goal was with local feature, so indirect tracking was second priority. Is not optimized for real time, and I would say that it's quite difficult to do that with Python, but that's my opinion. And more parameter auto-tuning would be nice to have. And probably this is more research related, how to integrate and unify end-to-end SLAM methods that are coming out with the old modular design. So there are some lessons learned, probably some of them are not surprises. So good features are not necessarily good for SLAM. So what it means is that if you take some local features and you test them in the context of image matching of place recognition, and then you plug them inside the SLAM, the results that you get are not necessarily good. So it means that when you integrate one module and you test it inside a full pipeline, you can get many insights and you can uncover some unexpected limitations. That is my experience, at least. Of course, community feedback is invaluable, and I met many friends, and I learned a lot from questions, and of course, bug fixed contribution and so on. Future work, more camera models, of course, improvements to the install process, full LiDAR visual inertial baseline, more parameter auto-tuning, and integrate and unify modern end-to-end paradigms would be a nice thing to have. So just quickly mentioning slamplay because I ran out of time. Slamplay is a C++ ecosystem, is complementary to pySLAM. It's a single CMake framework that integrate many libraries. So very quickly, on the front end, we have very classic OpenCV, libpcl tools, then SuperPoint, SuperGlue, SAM, HFNet. I mean, you can see the list without reading, and many backends, also loop closure. So basically all the models that we have in pySLAM, we have them also in slamplay. So the objective is basically to lower the entry barriers and create some unified library for developing and experimenting with SLAM in C++, of course. So pySLAM and slamplay aim basically to make SLAM development faster, cleaner, and more reproducible. You have the link, you know where they are, and you are kindly and warmly invited to contribute, test, and collaborate. I'm always happy to have feedbacks and also PR from anyone. Thank you.
Thank you, Luigi. Do you have any questions from the room for Luigi? Yes, go ahead.
Does pySLAM also support other sensors like IMU or wheel odometry and so on?
Not yet. That's the goal. I mean, for LiDAR, camera, and IMU, pipeline would be something very cool.
So I was wondering, because pySLAM came after, I mean, it follows VSLAM to structure. I would say that's like a mature SLAM system, right? So it came after, like, SLAM is like a mature field. So the overall architecture is mostly clear. All the like abstractions are clear. So when trying to apply this to other fields, do you think that it is important that first, like, the research field is mature enough so all these like nodes and connections are theoretically clear, or do you think that it could be started before? So to be more clear, do you think that pySLAM would have been possible before or VSLAM 2?
Oh, wow. I mean, I would say that VSLAM 2 and of course VSLAM 1 are like foundational, and probably some of the paradigms, I mean, the architecture is inherited from PTAM, of course, but there is a much, at least in my opinion, much more mature architecture, and of course, it was foundational also for pySLAM. I like it a lot, the approach of VSLAM 2, and you saw there is a lot of architecture that is inherited from there. But I'm not sure it would have been possible before that. I will buy your answer, your question, sorry.
Any more question?
Yeah, small question. Because pySLAM, it seems to be like a threaded. Is it deterministic, the results, whenever you run it?
That's an open problem, yeah. It can be deterministic if you remove the multiple threads. The problem is that determinism is not coming only from the operative system scheduler. It's coming also from many approaches that use random, like ransack. Yeah. So basically, on the Python level, you can instantiate the seeds of all these methods, but it's not enough because they are building on the top of C++ bindings, and you have to go down deep in order to also instantiate the seed in the component libraries. This is as far as I know. So it's kind of challenging, but it should be possible.
Practically speaking, one could just benchmark, like do multiple runs and then.
Yeah, it's tough to have determinism and also have repeatable results. I mean, with the evaluation.
Thank you.
That's a very interesting question. Thanks.
Thank you very much, Luigi. We have to move to the next speaker.
Yep.